Hello everyone, welcome back to EEE 641 Advanced Electromagnetic Field Theory. In today's lecture, lecture number 23, we are going to continue our discussion on scattering from the cylindrical structure. So if you remember in the last lecture, we considered the second polarization for the oblique incidence and we basically consider a scattering from a cylindrical structure under the oblique incidence of a plane wave with TE to Z polarization. Now, and at the end of the lecture, we also consider a line source in the vicinity of your cylinder. And specifically, if you remember, we discussed the electrical line source in the last lecture. So in today's lecture, what we will do is we will continue our discussion on line sources and scattering from the cylindrical structures. So in today's lecture, we will start with the magnetic line source as a source of waves, and then we'll see what would be the scattering from the cylindrical structure if we have such magnetic line source in the vicinity of the cylindrical structure. After that, we will see also some scattering from the apertures. Two types of aperture. One will be circumferential aperture and the other one would be axial aperture on the cylindrical structures. Along with that, we will also briefly review the results of GTD, geometrical theory of diffraction, UTD, uniform theory of diffraction, and compare those results with the modal solution as well as measurement results for cylindrical structures. We will also, along this topic, we will also look at the results for the spherical structures, even for conical structures when you have a source which is in the vicinity of conical structure, or let's say in the vicinity of elliptically cylindrical structure. So as of now, we have been discussing circular cylinders. We'll also see what do we need, what type of functions do we need in order to solve the scattering from the elliptical cylindrical structures. And in the end, we will focus our on the wedges. So as you know that in any complex structure, you might have a flat surface, which we already covered, that what would be the scattering from the flat surfaces like two-dimensional strip or rectangular plate or circular plate. These are some canonical structures. Then after that, we started discussing about the cylindrical structures, which is again some kind of curvature. So when we talk about this kind of cylindrical structures, what we are trying to do is, if you have some surface in your real time, in your practical application, you can always approximate some curvatures by either circular curved surface, or you can also approximate such surfaces, curved surface, using elliptical curved surface or elliptical cylinders. So those are the another canonical structure which we discussed. Same way, there are other two canonical structures which usually you can use in explaining the scattering from the complex structures. You can decompose your complex structure into this building blocks. You can call this structures as a building block. So other two structures, such structures are wedges. Basically, whenever you have some kind of edge, so something like this. So something like this. So if you have something like this kind of structure, and if you have an exterior source, then what would be scattering from this kind of edges? So for that also we'll look at the derivation, how to form solution from for such structures, for the scattering from the such structures. Also another very important building block is the corners. So something like this. So if you have a say dihedral corner, something like this, or this is the dihedral corner. Now something like this, if you have additional one plate, so this is your surface one or plate one, this is plate 2 and plate 3. If you have 3 surfaces, then it will form trihedral corner. So these are some of the building blocks. So what I was saying that towards the end of this lecture, we'll start discussing this topic, which is nothing but wedges. So let's start our lecture by discussing on cylindrical structures, scattering from the cylindrical structures, especially when you have a magnetic line source. So again, this is the geometry which we considered, where you have a length of cylinder along the z-axis. So your cylindrical structure, which is nothing but a scatterer in our case, is placed along z-axis at origin, and it has a radial dimension of a. Okay, and this prime coordinates rho prime and phi prime denote prime coordinates denote the direction and the location of your line source. So here in this case, here we have electrical line source which carries a current is, and it is located at rho prime radial distance from the z-axis, and it has a phi prime angular displacement from the x-axis. So that is the electrical line source, and then this is our observation point O, which is whose location and direction is denoted by unprimed coordinates. So in our case, unprimed coordinates are rho and phi. Okay, so rho and phi defines the define the direction and location of your observation point. Again, this is your top view of the same geometry, same structure. So again, you have a cylindrical structure at origin along the z-axis. Then this is your line source, and this is your observation point. Okay. Now, if you remember, when we have electrical line source placed at a quarter wavelength distance from the surface of the cylinder, that is nothing but, let's say this is your cylindrical structure and this is the surface. So this is your cylindrical structure. Okay. So this is your cylindrical structure and this is the surface. So from the surface of the cylinder, okay, we have a line source here, placed here, and the distance from that line source to this cylindrical surface is lambda by 4. That is nothing but quarter wavelength. So what we are doing is we are considering a cylindrical structure having a radius of curvature of phi lambda, and the line source is placed at the rho prime equals to 5.25. So if we take a difference of that, basically the distance between the surface of the cylinder and the radial distance for the line source from the origin is 5.25. So difference is 0.25 lambda. That is nothing but lambda by 4 distance. So if you remember, we showed last time in the last lecture, lecture 22, that when we have quarter wavelength distance between the line source, which is parallel to the surface of the cylinder, then what happens is the direct waves which are being radiated from this line source and the waves which gets reflected back from the cylinder and again get scattered in the x direction, they create a constructive interference in the positive x direction, in the and around the x direction. So as a result of that constructive interference between your the original radiated field from the source and the scattered field from your cylinder, because they create a constructive interference, that's why you see a maximum radiation here in the broadside direction. That is nothing but a positive x direction. So let me just clear out this slide. So as you can see that here you can see that you see a maximum radiation or maximum scattering, whatever you want to call, in the broadside direction, because your scattered field and directly radiated field from the source, they create a constructive interference in that direction. They are in phase, and we showed why they are in phase in the last lecture. Similarly, instead of that 0.25 distance, Now let's say that you move your line source to 5.5 lambda, that is the difference between this and this, between the line source and the surface of your cylindrical structure is 0.5 lambda. And as you can see that when you have that 0.5 lambda distance between the line source and the surface of the cylinder, it creates a destructive interference, and we showed that last time that how they create a destructive interference. As a result of that destructive interference between the scattering field and the original direct radiated fields from the source, you create this kind of null in the broadside direction. Now again, let's just go back one slide to this particular case where you have 0.25 lambda distance from the surface of the cylinder. What happens is when we have A equals to 5 lambda, you see that you have some kind of back radiation on the back side of your cylinder, on the rear side of your cylinder, and that is primarily because you have there is some kind of uh, waves. There are some waves. So this is the shadow region, right? If you remember, we call this as a shadow region behind the cylinder. This is a shadow region. So in this shadow region, what happens is usually your scattered field and incident field, they cancel each other out, because your scattered field are going to be 180-degree out of phase with your incident original waves. And as a result of that, what will happen is uh, you will see a shadow. You will see almost uh, no field, no total field on the backside here, and that's why it creates shadow. Now what happens is when your cylindrical structure has a very small radius of curvature, okay, so here let's say it is simply just 5 lambda. In that case, what happens is there are some additional waves which gets attached to the surface of your cylinder, okay. So let's say here they get attached to that surface, and then what happens is they travel along this surface, along the circumferential surface like this. And when they travel along this circumferential surface of the cylinder, along that travel, they keep on radiating some energy. They keep on leaking away some energy in this fashion. And those, as a result of that, what happens is there is this kind of leakage from one side, and similar type of leakage happens from the other side. And due to that, because there are two types, there are this multiple locations from which you see this leakage, they create a constructive and destructive interference on the back side here. And as a result of that, you see some kind of lobes on the back side. You will see some kind of radiation on the back side. So when you have a 5 lambda, you see some kind of back radiation. However, what happens is if you have A equals to infinite, that is radius of curvature is infinite, that is nothing but a flat surface, okay, because your radius of curvature is so large, you can consider that locally this surface is nothing but a flat surface. So for flat infinite surface, you don't see any kind of radiation on the back side or rear side. So let me just again clear out this slide. So what I'm trying to say is, if you can see, if you focus on this dash line, which is A equals to infinity, you can see that there is no radiation on the back side, right? There is no radiation on the back side, and that is because you have an infinitely large cylindrical structure. So that's why you create a proper shadow. You create a proper shadow in the rear side of the object, or rear side of your cylindrical structure. The same thing you see for the when you have a, 0.5 lambda distance between the line source and your cylindrical surface. Again, you see that when A equals to infinite, radius of curvature is infinite. Again, you see that you don't have any kind of radiation on the back side or rear side of your cylindrical structure in the shadow region. Now, that is what we discussed in the last lecture. We showed these results. We actually derived this in the last lecture. Now, same thing we can do for the magnetic line source. Now, when we say magnetic line source, basically we have some line source which carries some magnetic current and it is placed parallel to z-axis, or it is in general placed parallel to the axis of your cylindrical structure or along the length of your cylindrical structure. So here you can see for the electrical line source that here we have a electrical line source which is parallel to the length of your cylinder, and it carries IE electrical current, and this is the case which we considered last time. Now what we will do is someone can ask that, okay, instead of IE, now we are going to have IM. Okay, we are going to have IM, but usually you would not find any practical scenario where you would have a magnetic line source. So question may arise in your mind that why would you require such kind of scenario, where would you see application for such kind of problem? So this is one of the practical example, where you have a thin slot on a PEC, perfect electric conducting cylinder. So what you can have is something like a cylindrical waveguide, let's say cylindrical waveguide, which we saw, which we studied, in which we investigated in chapter 9. You can have this kind of slot in the z direction along the length of your cylinder, and what you can do is in that slot, okay, in that slot, the fields which you have, let's say electrical fields which you have in that slot, which is nothing but radiating, and you want to find what is the radiation, or what would be the radiation pattern of this kind of antenna, where you have a waveguide and you have created a slot, and you want to use that as a, let's say, antenna radiating element, then how would how will it radiate, what would be the radiation pattern? Then in that case what we can do is let's say that we have this E field distribution, which is nothing but a uniform E field distribution, because the slot is very thin in the phi direction. Okay, from that we can find what would be the equivalent magnetic current density, okay, using this equation, and from that we can write down what would be your equivalent current density. So that will be your equivalent magnetic line source placed right on top of your circumferential surface. So now you have that magnetic line source placed right on the top of your cylindrical surface along the length of your structure. And basically that is what we are going to solve. This is one particular specific case where you now place your that line source on the surface of your cylinder. That means that you are trying to create rho prime, that rho prime which defines the location of your radial location of your line source is equals to A, which is nothing but a radial dimension of your cylinder. So again, this is your generic geometry, where, as I mentioned, that these prime coordinates denote the location and the direction of the line source, whereas this observation point is defined, or this unprime coordinates, let's say this unprime coordinates rho and phi represent the direction and location of the observation point. So this is a generic definition which we are considering. So we have a displaced line source compared to from displaced line source from the origin of the coordinate system, but still it is parallel to z-axis. And why are we consider displaced line source? So if you remember, as I just showed in the previous slide, we are going to place our scatterer, that is nothing but a cylindrical structure along the z-axis at the origin, and that's why we require a line source which is displaced from the z-axis. So we have derived the expressions for this kind of line sources, both electrical and magnetic line sources. And we saw that for such displaced line source from the z-axis, the radiated field can be given by this expression. This is for magnetic line source. This is nothing but TE to Z polarization. Okay, this is a TE to Z polarization. And if you remember, it is given by the Henkel function of the second kind, Henkel function of the second kind with the displaced argument of rho minus rho prime. Now again, we have derived and we have gone through this addition theorem of Henkel function, that if you have a Henkel function of second kind with a displaced argument, how can we write that Henkel function with a displaced argument in terms of infinite summation of Bessel function and Henkel function? So if you remember, for that we divide our observation region into two regions. Region 1, where your rho is less than or equal to rho prime, that is the first region, and the second region is when the rho is greater than or equal to rho prime. So for the first region, since our most of the waves you expect it to be bouncing back and forth in the radial direction, that's why we use Bessel function, if you remember. So, right? So with respect to rho, here you will see a Bessel function of the first kind. Why don't we use second kind? Because it has a singularity at the origin. So we want to avoid that kind of singularity in our field distribution, and that's why we get rid of the Bessel function of the second kind. So that's why we use only Bessel function of the first kind. So we impose that additional boundary condition. Similarly, for the second region, as we saw that in the last lecture, that for the second region, since most of the waves you expect it to be getting radiated away in the radial direction, we usually represent it using Henkel function of the second kind in the cylindrical coordinate system. Again, we don't use Henkel function of first kind, because Henkel function of first kind represents the waves which are incoming towards the origin of your coordinate system, here cylindrical coordinate system, right? So that's why we use Henkel function of second kind for the second region. And then if you remember, basically we equated these two equations, expressions, when rho is equals to rho prime. Since your fields have to be continuous, so at rho equals to rho prime, this expression and this expression should give the same result, same expression. They should reduce down to same expression. So from that we were able to find what should be the these functions, and as a result of that we were able to derive the two different expressions for two different regions. So I highly recommend you to go back to last lecture or even previous 2-3 lectures in order to get the physical insight about addition theorem of Henkel function. So that is the incident field. That is nothing but the radiated fields from the line source which is displaced in from the z-axis. Now similarly, again, what we did in the electrical line source case, here also for the scattered field, we know that fields are going to be leaving the z-axis and they are going to travel in the radial direction. That's why we are going to use Henkel function of the second kind. Something similar what we did for the incident wave. For the scattered waves, for the scattered field, we are going to only use the Henkel function of second kind. Again, here we don't know that what would be this unknown coefficient, because it's not only going to be Henkel function of second kind, it has to also satisfy the boundary conditions, and that's why in order to able to satisfy that boundary condition, we have this unknown function or unknown coefficient which we haven't derived yet, that the expression of that unknown coefficient or function which we haven't derived, but we will derive using by imposing the boundary conditions for our given problem. So again, we have the infinite summation of the Henkel function of the second kind for the scattered field. Now the total field, when we add this incident and scattered field, the total field again can be given by these two expressions, okay, for two different regions. So this is for the region 1 and this is the scattered component, this is the incident component. Same thing for the second region, where you have this one coming up from the incident component and this component is coming from the scattered component. Now Using the Maxwell's equation, we can find the corresponding E components. So we now have this equation from where we can get the expression of E rho component, radial E field. Now, this is the total E radiated in the total E field in the radial direction. And again, you have two expressions for two regions. Okay, this is the first expression, first component. Similarly, you can also find the another component E phi. So this is the expression for the total E phi component. Again, two expressions for two regions. Now here we will be more interested in E phi component. Why? Because E phi component is nothing but a tangential component to the circumferential surface of your cylindrical structure. So along the phi direction, your total E field should vanish because you have a PEC surface, PEC structure, perfect electric conducting surface, right? So for PEC surface, we know that the tangential component of your total E field should go to 0. So we will impose that boundary condition at rho equals to A. At rho equals to A, we will make this E total phi equals to 0. When we do that, when we impose this boundary condition at rho equals to A, by adding incident and scattered field, you will be able to come up with the expression of the dn. So this is the expression of the dn which we can derive using by imposing this boundary condition. And when we substitute that definition of dn, this will be your final expression for hz. Okay, hz total field. Now once we have this hz, what would you do next? You can find the what will be the induced current density on the surface of the cylindrical structure. So again, we can substitute the expression of dn in other two components, E rho and E phi. So these are the components which we have for E rho and E phi. And this is the hz. Okay. Now, as I mentioned, using that hz, we can find what would be the induced surface current density on the surface of the cylindrical structure when you have rho equals to A. So n cap cross ht at rho equals to A will give us that expression for the surface current density. And when we do that, you can see that you will have surface current density in the phi direction. So basically, the induced current density, if we just go back, and this is your final expression. So this is the, when you substitute the expressions for hz, this will be your expression for the js, which is going to be in negative a phi direction. Okay, negative a phi direction. So if we go back here in this geometry, okay, so this is your phi direction, right? Which is basically coming out of x-axis. So your js is going to be in this direction. Js going to be in this circumferential direction, like this, in the phi direction. This is the induced current density when you have a magnetic line source in the vicinity of your cylinder. Okay. And from that, we can find what would be the scattering from your structure. We have already derived that H total and E total, right? Once we have that H total and E total, what we can do? So since we have here H total, if we want to find what would be the, let's say, scattering field in the far field, what will we do? We will apply the asymptotic expansion for the Henkel function, right? So let's go to this surface current density. So this is your surface current density when you substitute the expression of your Hz. Now, after manipulating this numerator and denominator, we get this form. Again, if you remember, we have used that even in the last lecture. This is nothing but Wronskian of your Bessel function. And we know now that Wronskian of the Bessel function has this particular value, which you can see on the right hand side of this equation. So what we will do is we will simply substitute that value here, expression here, and by doing that, this will be your reduced expression of the induced surface current density. Okay, so this will be your final expression. Now, as I mentioned that once we have this E total, H total, the next step would be to find far field scattered field. And for that, basically your beta rho, your observation point is now in the far field. So beta rho is much larger than 1. And when you have this argument beta rho, which is much larger than 1, we can use that asymptotic expansion for the Henkel function. So in this Henkel function, in this definition of hz, we'll apply this asymptotic expansion, which is nothing but in terms of exponential function, right? That represents a radiating field in the rho direction, right? Traveling waves in the positive rho direction, and we have used this for many times, right? So this will be your expression for the hz field approximately in the far field. Now the next step is what we just showed, that one of the application is when your magnetic line source is placed right on the surface, right on top of the surface, cylindrical or circumferential surface of the cylinder, along the length of the cylinder, along the axis of the cylinder. And when you have that kind of case, it is equivalent to having a thin slot on the PEC cylinder. So if you have a thin slot which is radiating energy, electromagnetic waves, then that is equivalent to having a magnetic line source placed right on top of the cylindrical surface, and that is making rho prime equals to A. So when we make rho prime equals to A, when we set the location of line source to be equals to A, in that case, this will be your hz. So this is your this is going to be your hz. What we are doing is rho prime equals to A, and again by using the Wronskian, and by manipulating these terms, this will be your reduced form of hz in the far field. This is again in the far field, right? This expression has exponential function. Okay, so keep in mind. So what we have done is we have moved our observation point in the far field, that is rho, beta rho is much greater than 1. So it's in the far field. Our observation point is in the far field, and at the same time we made or we moved our point source to the surface of the cylindrical structure. And when we do that, this will be your reduced equation or expression for the far field magnetic field, which will have a z component. Okay, and when we plot that, this is the plot you will get for the radiation pattern. This is the radiation pattern for this structure when you have a very thin axial slot on a circular conducting cylinder. Now we have shown two cases here. One is A equals to 5 lambda and the other one is A equals to 2 lambda. Again, as you can see that as we keep on reducing the radius of curvature, you will see more and more you will see more and more backside radiation or on the rear side of your cylindrical structure, and that is nothing but due to the diffraction from the curved surface. And that diffraction we explain through the creeping wave mechanism. So the creeping wave is a way or is a mechanism through which we try to explain the diffraction from the curved surface, and we use that in GTD and UTD. So what happens is, this is your location of your aperture. This is a slot, okay, here. So there are some waves which are getting radiated from this slot, and along with that, some waves are going to travel along this surface, and then when they travel along the surface, they will continuously lose their energy by radiating some waves or radiating some energy, by leaking some energy. And that is this kind of waves which are basically getting attached to your surface and travel along the cylindrical surface or circumferential surface is called the creeping waves. And as I mentioned that you will have this kind of leakage or this kind of creeping waves from the both sides of your cylindrical structure. As a result of that, they will add with each other and create constructive and destructive interference in the far field, and that's why you see this kind of lobes. You see these lobes on the back side because of the constructive and destructive interference from created by this creeping waves from the two sides of your cylinder. And as you can see, as we keep on reducing the radius of the curvature, so from 5 lambda to 2 lambda, when we reduce the radius of the curvature, that is basically you have more and more curved surface, right? It is more and more curved surface when you have a smaller and smaller radius of surface, radius of curvature. And as a result of that, for the dashed line, you can see that you will have more pronounced diffracted fills on the backside. You will have more or you will have larger backside radiation or radiation on the rear side of your cylinder. Now something similar in example 11.4, what we do is we consider two types of apertures. One is a circumferential aperture and the other one is a axial aperture. Now based on how their larger dimension of aperture is directed, okay, we'll see that. And what we'll do is we'll see the expressions for those kind of aperture. When you have those kind of aperture, what would be the radiation from those apertures? We are not going to go into the detail of the derivation, but we'll see and we'll compare those results with aperture when they are placed, both the apertures, circumferential aperture and axial aperture, when they are placed on the flat infinite PEC ground. So we'll compare those two cases. So as you can see that this is the, we are going to have these two cases. So let's go to the geometry. So this here you can see that the larger dimension is along the circumference of the cylindrical structure. So that is nothing but a circumferential aperture. In this case, in the second case, the larger dimension is along this axial direction, along the length of your cylindrical structure, and as a result of that, this kind of aperture can be called axial aperture. Now if you look at the field distribution, and you can explain this field distribution from the field distribution of the dominant mode for the rectangular waveguide. If you remember, for rectangular waveguide, for TE10 mode, we had something similar field distributions, right? So since this is an aperture having a rectangular shape, it will have a similar field distribution, since it has a PEC edges on the four walls, right? It has a PEC edges on the four walls. And we have gone through this in chapter 8. So this should be obvious to you. Now, as you can see that for the circumferential slot or circumferential aperture, your E field is tangential to the shorter side of your aperture, right here. And that, as a result of that, in this plane, in this XZ plane, that is nothing but azimuthal plane, in this particular coordinates, in this particular setup, along the XY plane, along the XY plane or azimuthal plane, we can call that as a circumferential plane as well, or we can call that as a H plane, horizontal plane. We can call that as a horizontal plane. In that horizontal plane, since your E field is tangential to these two edges, let me just use highlighter, these two edges, right, vertical edges, right? As a result of that, E field gets vanished, and as a result of that, these two edges are nothing but soft. So this polarization is kind of soft polarization for those two surfaces, and which will result into very narrow beam width in the H plane. So along this plane, along this horizontal plane or circumferential plane, or even if you look at this E vector, so E vector is like this, right? In the XZ plane, it's parallel to XZ plane. So XZ plane is going to be your E plane, and this XY plane, which is orthogonal to that, is nothing but H plane. So in the H plane, so this is nothing but H plane, right? Horizontal plane or H plane or circumferential plane or azimuthal plane. In that plane, since you don't have that much of diffraction from the edges, if you remember, we discussed the horn antenna, and at that time we also had similar discussion that since your E field is parallel to your edges, okay, as a result of that you will not have that much of a diffraction from those two edges. However, if we look at the other two edges, these two edges, if we look at these two edges, okay, in the vertical plane, your E vector, this E vector is orthogonal, is perpendicular to the edge of those two edges. You will see a lot more diffraction, and as a result of that diffraction, you will have a much broader beam width in the vertical plane, that is along this XZ plane, In the vertical plane, you will have a lot broader radiation pattern. And on the other hand, if you look at this geometry, that is of the axial aperture, in this case your E field is parallel to the same aperture's edge. So in the vertical plane, your E field is parallel to this edges. As a result of that, you will not have that much of diffraction in the vertical plane. So in vertical plane, for the axial aperture, it will have a narrow beam width, narrow radiation pattern. So on the other hand, in this horizontal plane, okay, now this horizontal plane is nothing but E plane, since your E vector is parallel to your XY plane. So that horizontal XY plane is nothing but E plane. Here that horizontal plane was nothing but H plane, and here vertical plane was E plane. Here in the axial aperture, this vertical plane is a H plane, since E field is perpendicular to that plane. So it is a H plane. Now, in the H plane or vertical plane for the axial aperture, it is going to have a narrow beam width because it has a E vector which is parallel to the edge, and resulting into the lesser amount of diffraction towards the edges. So, and that's why you will not have much broader or much wider beam width in the vertical plane for axial aperture. However, in the E plane, in the horizontal plane, since your E vector is perpendicular to these two edges, okay, these two edges, as a result of that, it will have a much more pronounced diffraction from those two edges, and it will have a much broader beam width in the azimuthal plane or E plane or horizontal plane. So this kind of like, how do we create, what type of aperture shall we use, is the choice is oriented by choice is made by the or dictated by the desired polarization, what type of polarization we are looking for, okay. And this kind of cylinders, you can consider that these cylindrical structures are part of, let's say, some aircraft, or missiles. Those kind of structures, like this kind of cylindrical structures, are part of those practical structures like a missile or airplane or aircraft. And you can see that if you have that cylindrical structure as a aircraft, then you would like to have a pronounced or a proper radiation in the forward side of your cylinder or forward side of your aircraft, so that when you use this microwave landing system, MLS, you would like to have much more radiation in the forward direction, so that it can this microwave landing system can work properly. So what will happen, that you have this let's say a cylindrical aircraft. I'm just simplifying the problem, okay. So let's say you have a cylindrical structure, which is nothing but, let's say, your aircraft or missile or something. And let's say if you are using some microwave landing system, then you would have something like a transmitter and receiver in the forward direction, right? In the forward direction here, somewhere in your airport, right? Where you are trying to land. So you would like to have maximum radiation or proper radiation in the forward direction, and that can be achieved when you have a broader beam width, in the vertical plane. And that can be achieved here in this case by circumferential aperture, right? In the circumferential aperture, since our diffraction was more pronounced in the vertical plane, you will have a much broader beam width in the vertical plane. So that's why you would prefer this circumferential aperture over this axial aperture in that particular case. And again, using the same analysis which we did for rectangular waveguides, we know that for circumferential aperture, your E vector will be in Z direction, as we just showed in this figure. For this one, your E vector is along the Z direction, right? It is along Z direction. And for this axial aperture, your E field is along the phi direction. And for that, this will be your expressions for E field for circumferential aperture and axial aperture. Now, once we have this, we can find what would be the far field radiated fields from such apertures with this kind of field distribution. Again, this is the geometry, and let's say that our frequency, operating frequency, is 10 gigahertz, and we have a X band waveguide dimension, that is W equals to 2.286 and H equals to 1.016 centimeter, and that is the dimension of your aperture. And we want to find what would be the radiation pattern for the circumferential aperture in the H plane. In the H plane, that is basically you have you are interested in the horizontal plane radiation pattern, and same thing you want to find what would be the radiation pattern in the E plane of your axial aperture, that is again nothing but your horizontal plane. So again, the cylindrical structure which we are trying to investigate are having a radial dimension of A equals to 2 lambda and A equals to 5 lambda. So when we do that, we have two methods through which we can find the radiated fields. First method is we can approximate our current densities, Js and Ms, equivalent current densities over the aperture, and then integrate using the integration over the aperture and the surface of the cylinder, we can find the what would be the far field radiated fields. Now, the Js is known inside the aperture. Okay, over the aperture we know what would be the distribution of your Js and Ms, but we don't really know what would be the expression for Js outside the aperture. And what we will do is either we can do that we can assume that Js is smaller outside the aperture, and we can ignore it kind of, and we know that this is not the exact equivalent. Another equivalent is to assume that Ms is only and only over the aperture. So existence of Ms is only over the aperture, as done for the apertures mounted on the ground plane. So what we are saying is you can approximate, you can assume that your Js and Ms is not significant outside the aperture, and with those assumptions we will be able to find what will be the radiated fields in the far field from this apertures. So that is one particular method. Okay, that is one method. The other method is what you can do is the fields outside the cylindrical structure are expressed in terms of sum of the TE to Z and TM to Z mode. So first we represent those fields external to cylindrical structure in terms of sum of the TE to Z and TM to Z modes. And once we do that, again, those things can be achieved by writing down the expressions of FZ and AZ, which we have done, right? We have been doing this for TE to Z and TM to Z polarization, we have defined first what would be the vector potentials FZ and AZ, and then from that we were trying to derive the expressions of what would be the E and H fields. So we can follow that procedure as well. So you can see that again you can go back to field chapter 6 and follow that procedure, and you will be able to find what would be the far field using the transform techniques. When you do that, this will be your expression for E theta and E phi for the circumferential aperture in the circular cylinder, and where basically epsilon n is nothing but a Newman coefficients, which has two values for two different conditions. When n equals to 0, it will be 1. When n is greater than 0, it will be 2. And again, when theta is equals to pi by 2 and phi equals to 0, your E phi is going to be 0. Similarly, your E theta is going to be 0 for your axial aperture on the cylindrical surface, and E phi is going to be non-zero. It is given by this expression. You can derive that. And again, E theta is 0 in all plane as we expect. Now, what you can do is, what we will do is we will compare those two solutions with the apertures when they are mounted on the flat infinite ground plane. And for that, again, we have done this. We have gone through this practice in chapter 7, in the section 7.8 of the textbook. We go through this practice using the surface equivalent theorem. Okay, and again, when we have that circumferential aperture on the flat PEC ground plane, for the H plane, E phi is going to be 0 and E theta is given by this expression. And for the axial aperture, again on the flat PEC ground plane, in the E plane, E theta is going to be 0 now, and E phi is given by this expression, where C is given by this expression. Okay, now what we do is we plot both of them. And again, you can do this by this MATLAB code given by at the end of the chapter for chapter 11. The codes are given: PEC, cylindrical, plate, rectangular, and you can run that as well in order to plot your far field for this kind of structures. So you can see that when you have a perfect electrical conductor flat surface, then you see that you don't have any kind of radiation on the back side for this circumferential aperture in the H plane, which is nothing but a horizontal plane. And if you remember, for circumferential aperture in the H plane or horizontal plane, your E vector is parallel to edges of the aperture. So E vector is parallel to edges of your aperture. So if you look at here, I'm talking about these two edges in the horizontal plane. E vector is parallel to those two edges. As a result of that, you can see that here towards the grazing angle also, you don't have that much of radiation in the H plane, even for the infinitely large PEC structure, right? And same goes for even for the when you have a cylindrical structure with a radial dimension of 2 lambda and 5 lambda. Okay, so this is for the 2 lambda, this dotted line, and then this solid line is for the 5 lambda. So as you keep on reducing your radial dimension of the cylinder, you will see more and more radiation on the rear side or back side of your cylindrical structure. Now, for the other case, axial aperture, you can see that your E field is now perpendicular to these two vertical edges of your aperture, and as a result of that, it will create a more diffracted fields, and you will see a broader radiation pattern in this plane. And now for this case, it is going to be E plane. So you can see that for E plane axial aperture, again horizontal plane, now you have a very high radiation pattern or high radiation values even for the grazing angle towards this direction. You have a very high radiation for all three cases: for flat case, for the cylindrical case with 2 lambda radial dimension, and even for the 5 lambda radial dimension. Again, you see similar trend that on the back side, since now you have a much more stronger, you have much stronger diffracted fields from the edges, you see that those creeping waves get constructive and create a constructive and destructive interference, and you see back lobes creating some it this they create a back lobes in the rear direction on the back side of your cylindrical structure. Also notice that here these levels are somewhere around minus 20 dB, right? It is somewhere around minus 20 dB on an average, right, for 2 lambda. Now if you go back to the circumferential, if you look at this level, you have a perfect null here, okay? Even if, let's say, you consider this case, let me just clear out the slide. So even if you consider these particular points here, they are around minus 30 dB, and here on the proper backside it has a proper null, right? It has a proper null. So that's what I was saying, that if you have a circumferential aperture, and if you look at the H plane, in the H plane, since your diffraction is much weaker, as a result of that you will not have that much of radiation. However, when we look at this axial aperture, since your E field is perpendicular to the edge of the aperture, you will see a much stronger diffracted field, and that's why you will see a much larger and bigger back lobes. So that's what here you see, that's what he explains here, destructive interference, and basically it creates a greater number of lobes in the backside because of two creeping waves that travel in the opposite direction or around the surface of the cylinder. They create a constructive and destructive interference. So that is what we just showed. This is circumferential aperture H plane, and this is axial aperture E plane. Again, same thing can be seen for other two planes as well. So E plane for the circumferential aperture and H plane for the axial aperture. We haven't shown, but again we can explain the same thing for those planes. Now, after that, look at this particular geometry. So this is not a circular cylinder. This is a elliptical cylinder. So we haven't solved this kind of problem. We haven't considered elliptical cylinder yet. But in order to solve this kind of problem, you would require something like a Matthew function. Instead of Bessel and Henkel function, you will have to form your solutions in terms of Matthew function. So again, you solve using eigenfunctions. You will have eigenfunctions, and those eigenfunctions will be in terms of Matthew function. So they are again similar to Bessel function and Henkel function, but we are not going to go into that. And again, as you can see, this is the origin of your source, and in the front side, in this front side of your structure, where you have a direct as well as reflected fields in this region. However, on this back side, first of all, your scattered field and your incident field, they are going to be opposite to each other, and they will cancel each other out for the most part. So that's why you create a shadow. Okay, that is the first thing. That's why you create a shadow on the back side. And the other thing is, other than that, there will be some incident waves. Okay, there will be some incident waves which will get attached here. Okay, on this surface, scattered as well as incident. Okay, those waves will get attached on these points, let's say Q1 and let's say here Q2, and what will happen is they will travel along this surface and continuously will radiate in this shadow region from the both sides, and those are nothing but your creeping waves, and these waves are going to create some lobes in the shadow region on the back side or rear side of your cylinder. Same thing again, that's what here you see for the circular cylinder, that these are the creeping waves. Red and these green arrows, they represent the creeping waves from the opposite sides of the cylindrical structure, and they create a constructive and destructive interference in this shadow region. Same thing if you have a radiating slot on the cylinder. Instead of scattering, now we are trying to solve the radiation problem. In that case, as we just showed previously, that you will have this kind of clipping waves traveling along the surface, right? And they will also radiate, keep on radiating when they will travel along the surface and create a constructive destructive interference in the shadow region, and that's why you will see back lobes. Now, what are the applications? So one of the application, like again we haven't solved for the spherical structure, we haven't solved that yet. For the spherical structure, uh, it will again create a shadow on this backside of the structure, because your incident and scattered field going to cancel each other out. However, those fields which are basically getting attached to this surface, and that's what we use for explaining the diffraction from the curved surface, they create constructive destructive interference and create some lobes in the shadow region. And what you see is that if you plot a normalized RCS of a sphere, okay, normalized RCS of the sphere, let me draw two regions. So let me just draw first region. So here, when your circumferential dimension of the sphere, okay, circumferential dimension of your sphere with respect to wavelength, with respect to lambda, is smaller than 1, that means your circumferential dimension of your sphere, that is nothing but 2 pi r, right? That 2 pi r or pi d is smaller than the wavelength lambda. In that case, you will see a trend which is following a Rayleigh law for the scattering, okay? And we learned that in the high school physics, right? One of the main application of such type of scattering is scattering by the rain droplet for the light, So scattering by the rain droplet for the sunlight is a prime example of such structures, where the droplet size is much smaller compared to the wavelength of the light. Okay, there you will see Rayleigh scattering, uh, Rayleigh scattering, right? That is for when your circumferential dimension is smaller than 1. Now, when the circumferential dimension is equivalent on the range of the wavelength, or couple of wavelengths, that is like 2 lambda, 3 lambda, 4 lambda, something like that, in that range, when your spherical circumferential dimension is of that range, 2 lambda or 3 lambda or 4 lambda, then you see this kind of ripples or this kind of resonances in the RCS response, radar cross-section response of your structure, spherical structure. And that response is nothing but we call Mia scattering or Mia resonance, right? This is explained by Mia resonance. And again, we learned this in the high school physics. So this is nothing but the Mia resonance. And after that, again, as we keep on increasing the dimension of the sphere, that is this, when it keep on increasing, as we keep on going towards the right hand side on the x-axis, what will happen is, so in the beginning, as you can see in the beginning here, it was following the Rayleigh law, right? It was following the Rayleigh law. After that, in the second region, where your cylindrical dimension, circumferential dimension is comparable to your wavelength, that is 1 wavelength or 2 wavelength, 3 wavelength, some multiple wavelengths, okay? In that case, you see those kind of resonances, and that is nothing but Mia resonance. And after that, as you can see that, let me just change the color of the highlighter. As you can see that as we keep on increasing this, you will see that it approaches like this and it gets to one particular value for the normalized value, and that is nothing but the ratio of that sigma and pi a square is 1. That means at very large, for the large dimensions of the spherical circumference, for the large values of circumference, what I'm trying to say is for the large spheres where your circumferential dimension is much larger than the wavelength, your radar cross section, echo area or radar cross section is going to approach, or it is going to equal to the physical cross sectional area of your sphere, and that is nothing but pi a square. So when you take a ratio of that radar cross section or echo area, that is this sigma, okay, that is this sigma with respect to pi a square. When you take a ratio of those two, you can see that that ratio will approach to 1, value 1, as you keep on increasing the dimensions, circumferential dimension of your sphere. Okay, so this is one of the practical application, like for sphere. And here you can see that the solid line is nothing but eigenfunction method, right? That is exact method, and the other one is using geometrical theory of diffraction. As you can see that you get pretty good agreement between those two cases. So it's not only that geometrical theory of diffraction will give accurate answers when you have large dimensions, but it also gives very good answers for even small dimensions, and it can also predict the Rayleigh law, right? So the only difference is if you try to explain, if you try to come up with the eigenfunction method, it will have like an infinite summation, and it can take much more time compared to geometrical theory of diffraction, GTD, which can give you answer within a fraction of second. So again, GTD and PTD, all these methods are, or UTD, these methods are nothing but high frequency asymptotic methods, and which basically reduce down your computational requirements. So another, like other examples which we are not going to derive, but some other examples are, let's say you have a dipole antenna placed parallel to your cylindrical structure in the vicinity, and then if you look at for the electrical dipole, this would be the predicted radiation pattern by the GTD and UTD. Similarly, again for magnetic dipole, this will be patterns predicted by GTD and PTD, geometrical theory of diffraction and uniform theory of diffraction. Now you see that there are some discrepancies here, right? Here you can see that there are some discrepancies between the GTD and UTD. Now when we look at the comparison with the exact radiation pattern, right, you can see that UTD is actually much more accurate compared to GTD. So UTD gives much more accurate answers with respect to when we compare it with the GTD. Okay. Now, similarly, we can also consider something like an elliptical structure, elliptical cylinder. Okay, this is an elliptical cylinder where in one direction it has a dimension B, and in the other direction it has a dimension A. Okay, so it's an elliptical cylinder, and when you have a dipole antenna, magnetic dipole antenna, which is placed parallel to that cylindrical structure, then this will be your radiation pattern. One of them is UTD, uniform theory of diffraction, and the other is method of moments, okay, which is supposed to be more accurate. So you can see that they are pretty much in agreement. They are in well agreement with each other, right? Again, this is another example where you have axial slot on the cylindrical elliptical cylinder, and that axial slot is here. You can see that. So longer side is along the axis of the cylinder, and you can see that again you have a very good agreement when we compare with the experimental results, theory and experimental results. You get a very good agreement. As I mentioned that for this kind of structure, again you can derive the exact solutions, okay, But as I mentioned that you will have to use a Matthew function when we try to solve this kind of elliptical cylindrical structures. You have to use Matthew function, which is again similar to what we use for what we use in the case of circular cylinders. When we try to solve those structures, circular cylinder, we use Bessel function and Hankel function. Similarly, Matthew functions have to be used when we solve structures, elliptical cylindrical structures. Then another case is where you have a electrical dipole placed near to the conical structure, and these are the predicted and measured radiation pattern in the azimuthal plane. Okay, so you can see that they are in good agreements. Again, if you have a slot on something like a conical structure, here you can see that you have a radial slot along the radius of your conical structure. This would be your results using GTD solution, uniform GTD solution, when we compare with the eigen solution, which is supposed to be more accurate. So this is like comparison of UTD, GTD versus modal, and you can see that you have a very good agreement. Same thing again here, right? You have a relatively good agreement when we compare with the measurement results. Now, this is the another topic which is very important, and we are going to go into detail for this structure. So that is scattering from the conducting wedge. So at the beginning of the class, I mentioned that we are primarily going to discuss two topics. One is a cylindrical structure with a magnetic line source, and then we'll also discuss something like slots, thin slot, then apertures, circumferential aperture, and axial aperture, right? And also we saw some other applications like spherical, conical, or elliptical cylinders. Now, another important topic is scattering from the conducting wedge. So, as I mentioned at the beginning of this lecture, at the beginning we showed this figure, right? So, for any finite structure, whenever you have a finite structure, you will always have edge, right? You will always have edges, and that edges scattering from those finite structure is nothing but scattering from conducting wedges. So this is again another classical canonical problem to be solved. We want to solve this problem and to have exact solution for that, so that when we have complex structures, when we decompose those structures into fundamental blocks like wedges or corners, or some curved surface like a cylindrical curved surface or elliptical curved surface, or let's say spherical surface or something like that, or flat plates. So we have discussed all those structures. Most of those structures we went through detailed derivation for most structures. Now this is another important structure, that if you have a finite dimension, you will always have the edge, and that edge is explained by scattering from those edges is nothing but scattering by the conducting wedge. So scattering of EM waves from two-dimensional conducting wedge has been very important problem to be solved since mid 1950s. Okay, mid 1950s, people have been people have been trying to solve this problem, scattering problems, and many of this work was done by J.B. Keller. Even in the last lecture, I mentioned his name, right? If you remember Keller cone, at that time I showed you that figure that basically it creates, when we discuss the oblique incidence on the edge of the, when we consider this conducting wedge and oblique incidence on that edge, the scattered field creates some kind of cone, and we call that as a Keller cone. That Keller cone, the name Keller, is named after J.B. Keller, right? So that Joseph Keller has contributed many of this work in 1950s, and what happens is many of the solutions were created in 1950s, and later in 1960s and 70s they were actually implemented and used in practical applications. So again, many of those work was done by J.B. Keller. And what you do is you first form the asymptotic form of solution by taking infinite series of the modal solution. Okay, that is what we do, right? We, if you remember, when we discussed this line sources, we represented the Hankel function in terms of infinite summation of Bessel function and Hankel function, right? And that's what even for this case we will do. We'll see that. And then what we do is we transform that infinite series of modal solution into integral solution into an integral by so-called Watson transformation. Okay, so here in this lecture we will first present the modal solution, okay, of the scattering by the wedge. Okay, and after that in the chapter 13 we consider the asymptotic solution. Basically we use Watson transformation and all those things to have the solution in terms of integral. Now again, for PEC wedge scattering, we will consider two type of sources. One is an electrical line source and the other one is a magnetic line source. So for electrical line source, if we go to the next slide, we can have two types of geometry. We can consider two type of geometry. One is basically when you have a reference at the bisector. So this is the reference of your wedge where you have a reference at the bisector. And the other one is where you can have a reference at the face of your wedge. Okay, so first we will derive expression for this one, and then towards the end we will transform that to this kind of case, and we'll see that how can we simplify the final expression when we transform from this to this coordinates. Okay, so let's start with this geometry. So in the phi direction, it has alpha angle on the both sides along the x-axis. So let's consider first of all the electrical line source. So as you can see that here we have an electrical line source IE, current carrying line source IE, displaced from the z-axis. It is parallel to z-axis and displaced by rho prime radial distance and phi prime angular displacement from the x-axis. So we know that using that addition theorem of Hankel function, that we can represent or we can divide that observation region in two regions. When one region is where your rho is smaller or equal to less than or equal to rho prime, and the second region is where rho is greater than or equal to rho prime. So for the first region, again we have showed that, and you know now by this time that we in the region 1 we will usually have Bessel function type of solution. So we'll have infinite summation of Bessel function, and along with that we'll also have this Hankel function of second kind. Okay, you can explain that using reciprocity theorem, or you can also explain that using, when we consider rho equals to rho prime, your field should be continuous. Your field should be continuous at rho equals to rho prime. Okay, and from that you can derive how can we come up with these functions. Okay, or here in this case this and this. And also for the second region, we already know that we will have only waves which are radiating away in the radial direction. So we'll use Hankel function of second kind for that second region. Now that is for incident wave, or the waves or fields radiated by the line source. Now when we form the total field, now what we will do is we will not write down the expression of the scattered field. Here in this case we actually know I should say that it is easier to first predict what would be the total fields, and then from that we can find what would be the surface current density. So what we'll do is we'll first assume what would be the total electric or total magnetic field for this particular line source. So this is the incident electric field from your electrical line source. Now we will assume what would be the total electric field, and for that, for again we will have two regions, region 1 and region 2, and again for the region 1 you will have Bessel function, infinite summation of Bessel function, and for the region 2 you will have Hankel function of second kind in the region 2. Now in addition to that we will have uh, additional functions. Okay, how do we come up with this additional function? Because we know that at phi equals to alpha and phi equals to 2 pi minus alpha, for these two angles, that is nothing but a tangential surface to this. This is the first surface and this is the another surface. Let me just clear out this. So what I was saying is we have two types of surfaces where your electric field, total electric field should vanish. That is this two surface at one phi equals to alpha, that is this surface, and the other one is when you have 2 pi minus alpha, that is this particular surface. So along those two surfaces, at phi equals to alpha and phi equals to 2 pi minus alpha, at those two surfaces total electric field should vanish. And in order to explain that, that's why we add this additional sine function. So we add this sine functions, sine v times phi minus alpha, and then sine v times phi minus alpha. So we have those two in these two expressions. Now you can see that when phi equals to alpha, right, what will happen? This will go to 0, and same thing, this will go to 0. Now in addition to that, we also have another function multiplied. And how can you explain this? So again, for this function we use the reciprocity theorem. So what does it tell? That let's say instead of let's say that if we interchange the location of your line source and the observation point, if we interchange the radial distance from the origin, that let's say rho is now your rho prime. Okay, whatever the value you had for rho becomes rho prime, and whatever value you had originally for rho prime becomes rho, then your expression should remain as it is. Okay, your solution should be as it is. And that's why when we replace those two, you will see that this phi should be replaced by phi prime, and again and that phi prime should be replaced by phi, and your solutions should remain as it is. And that's why from that you can see that we have to multiply this additional term. We have to multiply this additional term in order to satisfy reciprocity theorem. Also, similarly, you can say that this should be here. Okay, this should be here, right? And this should be equal to this one. When rho becomes rho prime and this rho prime becomes rho, so this f rho prime should be something like a Hankel function, and this Bessel function should be this g in the bracket rho, right? So what we do is, that's what we do. Or we can also think like this, that when we equate rho equals to rho prime, okay, when we make rho equals to rho prime, your field should be continuous. And when we do that, when we make that continuity, this expression should be equals to this expression, and from that we can say that this is going to be equals to this one, and from that we can say that this is going to be equal to this one, right? And this is going to be equal to this one. Okay, so that's what we get, that f rho prime will be Hankel function of second kind, and this G rho prime is going to be Bessel function of first kind with a beta rho prime. Also, this is going to be C equals to D. So these unknown coefficients dV and CV should be equal to each other, and that we define as AV. Now what we will do is we'll substitute all this in the original expression. So when we do that, this is your total EZ field, okay, total E field for this particular wedge. Now, and again with the electrical line source in the vicinity. Now there is one more unknown here which is left, that is AV. We want to find this unknown, okay. So as you can see that that is AV, okay, and there is also another unknown which I forgot. Another unknown is this V. So we don't know what are the values of this V and AV. So for that, what we will do is first we will apply that remaining boundary condition phi equals to alpha. So when we do that, your E total field should go to 0, and we know that it will go to 0, right, because this function is going to be 0 and this function is going to be 0, right. So you will not get any additional information out of that. However, when we look at the other surface, phi equals to 2 pi minus alpha, in that case you can see that we will be able to find the value of the or expression of the V. We will be able to determine the expression of V, and as you can see that these are the allowed values of M. M cannot be 0. As we have seen even in the previous structures, we always try to find what are the values for which you will get non-trivial solution, okay. If you take M equals to 0, it will give you a trivial solution, it will give you a null field, so it is not useful. So M cannot be equals to 0. M starts with 1 and then 1 2 3 and so on. Similarly, using Maxwell's equation, okay, we can find corresponding component of H rho, okay, and this will be your H phi, again using Maxwell's equation. Why do we find those? Again, from this what will happen is using this H phi component, we will find what will be the surface current density at the location of your line source, at the location of your line source, that is when rho is equals to rho prime minus and rho equals to rho prime plus. So that's what we will do is, so you have this Js equals to n cross H total. Now H total has two components, rho and phi. However, this n cap for the wedge is going to be, excuse me, so for that let me just go back to here. So what we will do is, in our case, what will happen is, let's say this is the, okay, I am not able to erase this. Let me find another figure where I can erase. Yeah, so you can see that this is the geometry which we are considering right now, right? So this is the location of your line source, rho prime and phi prime. So what we will do is, we can consider this as a cylinder, right, at rho equals to rho prime, right? We can create that cylinder, and on that cylinder, okay, in that cylinder, what we can do is we can find what is a surface current density you will get. What is a surface current density you will get here, okay, here. That will be the difference between the rho prime plus and rho prime minus, okay, that is this and this, outside and inside of that virtual cylinder, okay. That will give us the surface current density, okay, on the line source. So that's what we do is, so that's what we do here, that basically you have two components, H rho and H phi. However, that H rho that h rho is along the rho direction, right? And for that, this kind of surface, right, uh, the normal to the surface is also going to be in radial direction, so that is a rho. So this is arrow, they are parallel to each other, so that cross product is going to be 0. So you get rid of this h rho, so you now only have h phi component, and when we take a cross product of rho and phi, you get a z component in the cylindrical coordinates. So now you can see that your jas is going to be along the z axis, and is given by h phi of total, when rho equals to rho plus rho prime plus and rho prime minus. So that will be difference of that two. That difference will be equals to surface current density. Okay. So when you do that, you will get this expression, and that expression is again in terms of Wronskian. It is in terms of Wronskian, and we can use Wronskian of Bessel function. From that, your surface current density will reduce down to this expression. Again, we still don't know what will be the value of AV. That's our goal. We want to find that. Now there is another procedure which we can follow, that using Fourier series for the current impulse of amplitude IE, which is located at rho equals to rho prime and phi equals to phi prime, we can find what would be the surface current density, corresponding surface current density, and that will be given by this expression, right? This should be equals to this one, right? Again, this should be equals to this one, and when we equate these two, we get the unknown value AV from this expression. So AV will be dependent on the current value, current carrying line source IE. Okay. Again, we will use for the far field, we are going to use asymptotic expansion for the Hankel function for the second kind. So this is one of the expression, and this is going to be another. So we'll use both of this. So for the far field, beta rho argument is going to be much larger than, much greater than 1. Ideally it will approaches to infinity. So what we'll do is we'll substitute the asymptotic expansion for the Hankel function in the easy total field, and when you do that, this will be your expression for the easy total. Now further, what we will do is we can take this entire portion of the equation outside and can call it a function with respect to rho. So with respect to rho prime, you will have this infinite summation. You will have this summation, not infinite, but you will have this summation, and that will be your reduced equation, where Fe rho is given by this particular a chunk of terms. Now the other case would be when you have a plane wave incidence and want to calculate what would be the scattering from the wedge, and for that case your beta rho prime will approach to infinity, right? So for that case, basically when you have a line source in the far field, it is nothing but a plane wave incidence for the wedge, and for that now with Hankel function with this argument beta rho prime, we are going to use asymptotic expansion. Previously we used beta rho, we converted that Hankel function of second kind with the beta rho argument. Here this is beta rho prime, and when we do that, this will be your expression for the E total in the Z direction. So again we can also take some portion of this equation outside, and then the remaining will be this particular equation. Okay. Also, I think previously I made that mistake. Here actually you have this entire function and inside the summation. Let me clear out this entire slide. So this entire function is inside the summation. Okay. Same thing here also, entire function is inside summation, and this outside thing is given by this particular portion of the equation. So what we will do is we can consider some specific cases. Now we have what is the scattered field from this generic wedge. Now one of the specific cases when you have something like this half plane, right? So where basically alpha is nothing but 0 degrees. So you have simply half plane, something like this kind of structure, simply half plane, right? Where you have edge, it's like a knife. So it's like a knife wedge, okay? So for that, this will be your equation. It's an scattering from the knife wedge or half plane, and you can see that your V is reduced down to m by 2. Again, m is 1, 2, 3, and so on. And again, this will be your expression if you just substitute that values here, okay, and here, here, and here. Anyways, now another thing is we can show that let me just go to the plot itself, that we can consider two plates, two wedges. So first case, as I mentioned, is a half plane, which is highlighted by this black line, black solid line, right? Let me just highlight that using yellow. So this is your first wedge, simply a horizontal plate, right? Something like this, okay? That is a first case, and you can define that using n equals to 2. So in this expression, right, in this expression, right, when n equals to 2, when n equals to 2, basically your alpha is going to be 0. So it's a half plane, right? So that is this particular case where wedge angle, WA, wedge angle, that is 2 alpha, we call that as a wedge angle. And again, he has mentioned here, right, 2 minus n times pi. So that wedge angle is 0, that is a half plane case. And the other one is when you have a wedge angle 2 alpha equals to 90 degree, and that will happen when n is equals to 1.5. N equals to 1.5 will give you wedge angle equals to 90 degree, and that is given by this red line, okay? That is given by this red line. So let me just again highlight so that it is clear to you guys. So this is given by this portion and this portion, okay? So that is a 90 degree wedge, okay? So we will consider these two cases, and as I again keep in mind that we have considered psi prime equals to 30 degree, psi prime equals to 30 degree, okay, for a plane of incidence. So basically your line of source will be at psi equals to, phi equals to somewhere around 30 degree, and rho prime equals to infinite, okay? Phi prime is going to be somewhere around 30 degree and rho prime is going to be infinite, and that will create a plane wave. Now again, if you want to use this terminology, we haven't derived the expression for this geometry, okay? We created a geometry where you have this wedge which is symmetric to x-axis. Now here you see that x-axis is actually at the face of your x-axis is at the face of your wedge. Previously it was reference x-axis was at the bisector. So we will derive the expressions for that, but right now let's just see the results. So if you look at the results for n equals to 2, which is nothing a half plate, okay, half plane, and then n equals to 1.5. So for n equals to 2, you can see that solid line, it can go right up in the fourth quadrant. So this is the fourth quadrant, right? If we call that as a fourth quadrant, in that fourth quadrant, you see that there is some scattered field even in that region. Let me just use some highlighter. So here you can see that you have some radiation even there. However, for the 90 degree, that is n equals to 1.5, expressed here using or denoted using this dash line, it doesn't have any field in the fourth quadrant. It just have here till in the third quadrant. Okay. Right, but still you see that towards the end of that age, okay, so for both this 90-degree wedge as well as the half plane, you see that towards the end they go to zero, the fields go to zero. Why? The reason is here we have considered what? We have considered electrical line source which is parallel to z axis, and you know that your axis, your edge, okay, your edge is parallel to z axis, okay, which is parallel to. So here where is your axis, z axis? It is here, right? It is given here. So this is nothing but your z axis, which is going in or coming out of this plane. Okay, so it is your edge. This edge is also parallel to z axis, and at the same time your line source is also parallel to z axis. As a result, your line source, electrical line source, is parallel to the edge. And we know that we in electrical field we just derived, it has only z component, ez component, so it is parallel to the edge. And we know that when we have a E field parallel to the edge, then we don't have that much of diffraction, and that's why we call that as a soft polarization. Okay, soft polarization, because you don't have that much of diffraction. And since your for electrical line source, your E field, for electrical line source, your E field is along z axis, parallel to z axis. Your H field is in the xy plane, and as a result of that your H field is perpendicular or transverse to the z axis. So we can call this polarization as TM to Z polarization, TM to Z polarization. So this TM to Z polarization is also nothing but a soft polarization, and that is given by this electrical line source. It is generated by the electrical line source in the far field. Now, next thing is magnetic line source. So we have derived all these things for electrical line source. We can follow the same procedure for the magnetic line source. So now in the case of magnetic line source, we'll start with the Hz. So this is the total Hz. Again, we know that it will be similar to Ez. Now instead of Ez is just Hz. And instead of sine function, now you have a cosine function. Now you can assume, or you can also imagine, why do we have this cosine function, right? Because when we use the Maxwell's equation, we will have to take a derivation, and when we take a derivation, this cosine function will get transferred to sine function. And as a result of that, when we apply that boundary condition at phi equals to alpha and phi equals to 2 pi minus alpha, basically one of them is phi equals to alpha, for that particular phase of the wedge, your electric field will go to zero. It will go, it will reduce down to zero, or it will vanish, because you have to take one derivation, and that derivation you will differentiate this with respect to phi, that will give you sine function instead of cosine function for the E field. So that's why for H field we will take cosine function, and again from that, how do we write this another cosine? S times phi prime minus alpha. We use the reciprocity theorem. From the reciprocity theorem, that if we interchange the location of the line source and the observation point, your solution should remain as it is. It should not change. So that's why you have extra additional cosine of S times phi prime minus alpha function. And this is nothing but coming from the addition theorem of the Hankel function, right? We have gone through that. So this is your geometry. This is your geometry. And now, instead of this electrical line source, we will use magnetic line source. So this IE should be IM. Okay, this should be IM. So now we will have magnetic line source. And what will happen again? Consider this. If we move this magnetic line source in the far field region, since your magnetic field is going to be parallel to z axis, as we just showed that it has z component, right? H field has a z component. Your E field will be in the xy plane. E field will be in the xy plane. So now your E field is in the transverse direction to z direction, right? So this kind of source, when it is in the far field, the waves which it will generate, the plane waves it will generate for the wedge is called TE to Z polarization, because your E field is in the transverse direction to Z axis. So it's TE to Z plane wave and TE to Z polarization, right? And we will see when we will derive and see the expressions, we will see what are the results we get. So again, what is a practical solution for this kind of problem, or what are the application of this kind of problem? So we can have the electrical, we can have a aperture or a thin slot on the wedge itself at the phi equals to alpha. So when we have this kind of slot, we can find, we can equate it with the equivalent line source, magnetic line source having this magnetic current density M, which can be found using this expression, right? So we can have a equivalent problem where you have a magnetic line source placed right on top of the wedge at phi equals to alpha, right? And that will be given by this Im equals to Az times E0. Okay, so this is a practical application of that. If you have this something like a corner, okay, something like a corner of your, let's say, wings of your, let's say, consider a wing of your aircraft, okay, and it has this kind of wedge, okay, some sharp corner, and if you have some kind of aperture or slight opening, thin opening slot, and if you want to use that as a radiator or something like that, I'm just giving you some random virtual example, okay, it's a fictitious example. This problem, this solution which will create can be used there to find the radiated fields. So again, using the Maxwell's equation, we can find the corresponding E field, and now you can see that we have these sign functions in the E field, right? So this is the E rho component. Similarly, we can also find the E phi component. However, before going there, here we want to use E rho component. Why? Previously for the cylindrical structure, we were more interested in EZ or E phi component, because EZ and E phi components were tangential to the circumferential surface of your cylindrical structure. Now here in this case, for the wedge, something like this, now we are interested in something like this kind of structure, right? Like a wedge. Now your surface of your face of your wedge is going to be parallel to your radial direction, okay, and that's why your E rho component is going to be tangential to the face of your wedge. So that's why we want this total E rho component to be vanished at phi equals to alpha and phi equals to 2 pi minus alpha. So we are more interested in E rho component. So we can find that E rho component using this Maxwell's equation, and then we can equate it to 0 for phi equals to alpha as well as phi equals to 2 pi minus alpha, those two boundary conditions, okay? When we impose that to those two boundary conditions, we already know that when we have phi equals to alpha, it is going to go to 0 because of that sine function. However, when we implement the other boundary condition at phi equals to 2 pi minus alpha, we will be able to find the value or expression of the S, right? Further, if you remember what we did for the electrical line source, we can find what will be the surface current density on the source itself using this electric field, and from that we can find that MS, okay, and again using that Fourier series, we can also find what would be the magnetic current density, and from that we will be able to find what will be the expression of the BS when we will equate those two. We are not going to go in the detail, but it's the same procedure, and where basically this epsilon S is nothing but a Newman coefficient, and that Newman coefficient has a value of 1 when S equals to 0, and it is a value of 2 when S is not 0. using that, in the far field zone, again, when beta rho is infinite, okay, when beta rho is infinite, it will lead us to far field radiated or scattered fields. And for that, this Hankel function of second kind with the beta rho argument, we can replace it with this asymptotic expansion, which is nothing in terms of exponential function. When we do that, we will come up with this total Z component for H field. Okay, this will be your H field. Now for plane wave incidence, as I mentioned, that you move your line source to infinite distance, and for that, what you do is you make this argument beta rho prime equals to, or it approaches infinite. When we do that, now Hankel function with this argument, we can write down corresponding asymptotic expansion for that. So this will be that far field approximate expression for the Hankel function of second kind. When we do that, that equation will reduce down to this equation. So this will be your scattered H field, when you have a plane wave incidence. Okay. Now, once we have this, what we'll do is we'll plot what would be the radiation pattern. Okay. And again, we can consider that half plane case, that alpha equals to 0, then S will become m by 2. Now m starts from 0. Okay, it gives non-trivial solution. Previously m was not 0, it was giving us trivial solution. For this polarization, it can give us a non-trivial solution. So these are the expression, reduced expression. And when we consider two cases again, half plane or knife wedge, and also 90-degree wedge, basically n equals to 2 and n equals to 1.5 in this wedge angle equation, then you can see that your fields are having a very high value even towards the edge. So for the half plane here, where you have the backside of your wedge, you see that your fields are very having a large values. And same thing also for the 90-degree, they are not 0. Okay, they are again very large value even for the 90-degree wedge in the shadow region, on the backside region. So your source is somewhere here, right, at 30-degree. So if you go back, source is at somewhere at 30-degree. So that means that you will have a shadow region like this. This is your entire shadow region for the half plane. Let me use the highlighter. So this entire region is a shadow region, right? So in the shadow region, you can see that here you have a very high value, right, for the half plane. So that half plane, basically, let me just highlight that values as well. So that is this particular curve, right? So that curve, you can see that even here you have a very high value, right, for the half plane. And same thing goes for the 90-degree wedge. Okay, even for 90-degree, you can see that you have a very high value in this shadow region, correct? So why that is happening? Think about it. It is happening because now you have a magnetic line source. Okay, magnetic line source. That means your E field is in the XY plane. Okay, it is normal to your axis of the wedge or corner, or that Z axis, right? It is perpendicular to Z axis. That's why this is TE to Z polarization. And as a result of that, since your E field is perpendicular to this edge of your wedge, basically you will have a higher value of the diffracted fields. And that's why you see in the shadow region, you have a very high values for the E and H field, scattered fields. Because it's a hard polarization, you have a strong diffraction from the edges. Okay, you have a strong diffraction from the edges, and that's why for magnetic line source, which is parallel to Z axis, that should be, you should keep that in mind, that not only magnetic line source parallel to Z axis. As a result of that, your E field is perpendicular to the edge. It is nothing but TE to Z polarization, and because of that, it is having a very pronounced diffraction from the edges, and that's why you see a very high radiation or scattering in the shadow region for both the cases. Now, at the beginning, when we started this topic of the wedge, we saw two geometries, okay? And what we will do is, these are the two geometries. So whatever expressions till now we have derived is basically for this geometry. What we can do is, we can transform this to this geometry, okay, by using this transformation. Okay, so we can use these transformations, and when we use these transformations, okay, so that is what we are doing here. So when we do this transformation, now your reference at the face, okay, this reference is now at the face x prime. Previously that x reference was at the bisector of the wedge. So when we do that, this will be your expression, and then from that you can get what will be the n. So n can be given by this. Now when n is greater than 1, it represents the exterior wedge. Why? Because when n is greater than 1, what will happen is 2 alpha is going to be less than, that 2 alpha is going to be less than 180 degree. So you will have something like this, okay? So this is the exterior wedge which we have seen in the previous slides. Now when your n is less than 1, what will happen? Your that 2 alpha angle is going to be greater than 180 degree. So now you have a case where basically you have something like this, okay, something like this. So this is nothing but interior wedge, okay, this is nothing but interior wedge, okay, this is the interior wedge. Previously this was the exterior wedge when n is greater than 1. So again, this will be this is given by this expression. When we implement that here, okay, this will be your expression for V. Now it is simplified to ratio of m and n, and where m is given by 1, 2, 3. Similarly for s, okay, similarly for s, again it is get reduced down to the same expression, but remember that m's value start from 0 for TE to Z polarization, hard polarization. Again, AV is given by this expression, BS is given by this expression. When we do that transformations, these functions you will see that can be written by this function, sine this function can given by this function, and this cosine can given by this expression. So if you look at these two expression, the only difference, now you have this negative sign, and now here you have a positive sign. So you can see that you gain some kind of symmetry. You have a common expression for both cases. So this was the previous expression for ETZ, and this is for HTZ. First one was for TM to Z polarization, soft polarization. Other one was for TE to Z polarization, hard polarization. And for the TM to Z, first or soft polarization, this will be your new expression, okay, for two regions. And similarly for TE to Z polarization, for hard polarization for two regions, these are the new expression in the new coordinates. And again we can combine them for the region 1. For the region 1, this will be expression for ETZ or HTZ. And similarly for the second region, these are the expression for ETZ and HTZ for TM to Z and TE to Z polarization. So basically what we are doing is we can combine those expressions together, and this is going to be your expression, combined expression for ETZ and HTZ for the first region, for TE to Z and TM to Z polarization. The only difference is negative and positive sign. With this epsilon m equals to 1 when m equals to 0, and epsilon m equals to 2 when m is not equals to 0. For the second region, this will be your expression again. Again, you have the same expression, only negative and positive terms is the main difference. And similarly, again, epsilon m has two values, Newman coefficient. And that's what basically, when we do this transformation, we can basically write down those expression, we can reduce down those expression, and we can have some common expressions for both the polarizations. And when we do that, basically we are able to write those common functions as a Green's function. You can write them down as a Green's function, and this terminology is primarily used in diffraction theory. Okay, in the diffraction theory they use Green's function, and we use that in chapter 13, which we are not going to go in detail in this course, but this is like something like you should know. Okay, so that Green's function is given by these two functions, right? Basically for two regions, okay, for both the polarization is given by two expressions, okay, and that is nothing but your Green's function. So you have a very common expression for ETZ and HTZ. That is nothing but this Green's function, and it is commonly used in geometrical theory of diffraction, GTD, this kind of terminologies. Again, as I've been mentioning, that TM to Z polarization is called soft polarization, and TE to Z polarization is called hard polarization. And this terminology is originated from the acoustic field of acoustics. So even in the acoustic, basically in the acoustic waves, you see this kind of diffractions a lot, right, in real time, from your doors or your windows, since your wavelength is much larger for acoustic waves compared to optical waves or electromagnetic waves, radio waves. Even for the large objects, large gaps, you will see a lot of diffractions, and that's why we hear sound from one room to the other room, right? So that is basically from this bending of these waves from the corners and the edges, or even from the gaps. So that's why they study even they also study this diffraction in detail, and they use this terminology soft polarization and hard polarization in the acoustics. And that's from where we get this terminology. For TM to Z polarization, we call that as a soft polarization, and for TE to Z, we call that as a hard polarization. So here we will stop our lecture. We will end this lecture here, but we will continue discussing this scattering even in the next lecture. We will continue discussing this wedges, and after that we will move to the next chapter for this course, that is chapter 15. Okay, till that time, all the best for your finals for the next week, and stay home, stay safe. Thank you. See you next lecture.